quick. Okay, so if you guys don't have any questions, so start with this little bit. All right. You guys can hear me?
Yes, we can hear you.
Okay, cool. All right. So so we're starting a new little unit here. So this is about projective. So this is about so the unit here. Let me just kind of give you like an overview of the unit. Okay, so this is about, you know, projective, injective, and flat modules. And they're essentially about the different functors. So there's a bunch of there's different functors you can do, and then depending on how these functors behave, we give modules names. And there's super useful and super ubiquitous. And so today I just want to talk about the Hom functor in projectivity and injectivity. So the Hom of our modules, projectivity and injectivity of modules. Not of maps, but of modules. We're not, so. Oh, how can we cut off? Oh, there we go. All right. Well, how come mine is being weird? Let me go back. Okay, there we go. Stop it. Stop it. Okay. That's my shirt. It's being a little wonkier than usual. Okay. So, all right. So let's first do the kind of first exercise. All right. So let's talk about the Hom. So morphisms. So let's talk about morphisms. Of our modules. Okay. So all right. So the key thing that gets all of this going is that you can add, if you have two R linear maps, so maps of R modules, then so the exercise, so maybe I can call this an exercise. So is that you can add, and actually you can multiply maps of R modules. Well, if they're endomorphisms. So you really, so let me just write this down. So maps of R modules are an R module. So if M, so let M and N be R modules. Okay, then this thing here, so mod R of Mn has the structure of an R module. Dang, it's being extra wonky today. Okay, so if we have two R modules, then this thing here, so recall that this thing here, mod, so this thing, so here, mod R. So this denotes the category of R modules. And then this thing here, mod R MN, this is the set of R linear maps between M and N. Okay, so R, of course, is a ring here. And so there's an alternative notation for this. Some people call this HOM RMN. So homomorphisms from R modules. Okay, and so the proof idea is pretty basic. Well, you just need to check linearity. Is that so? So one checks that for all C and R. Dang. For all C, what is going on, man? Okay, so for all C, geez. So for all C and R, that and all phi1 and phi2 in so these are morphisms of our modules that that this map I want to like see if my pen is working, so I'm tempted to like shake it out, but it doesn't work. That you know, could it be my battery of this thing? That that C, oh my goodness, that C, excuse me, C phi1 plus phi2, so this, we call this psi, is, oh man, I think it might, I'm going to see if it's my jacket. Maybe the static on my jacket is doing something.
Maybe, or like, we could even use another app today, if that works too.
Yeah, I might have to. Let me roll up my sleeve too. Okay, because like there's all this stuff down here. I'm wondering if it's my jacket. Okay, yeah, I might have to switch apps. That this map here, phi defined to be this way, is an R linear map. Okay, so this means that, and so so let me just take the definition. Let me show you the definition of Jesus Christ. Okay. All right, now I'm going to try and restart this and see if that fixes it. If not, I'm going to try and make a Miro board. Okay. Let's see if this does any better. Unlock. Okay. Okay, so we want this to be an R linear map. And so here, okay, psi of M is defined, so psi of M is defined pointwise. So you do C of phi of 1 of M plus phi 2 of M. This is for M and M. Okay, so the definition, the addition definition is pointwise. Okay. Okay, and so to check that it's R linear. So maybe I should say this. By the way, this is this. So the addition is pointwise. Okay, so what do you need to check? So we need to check that psi of Rm1 plus M2 is R psi of M1 plus psi of M2. Okay, that's what it means to be R linear. All right, so that's all I want to say about the proof idea. But all you do is you just, break out the definition, this definition here, and then you use linearity on each of these two pieces. Okay, so you use that this is linear, and you use that this is linear, and then you check that that you can just break it down like this. Okay. All right. So what this does is the upshot of this is that this now gives us two functors. Okay. So this is kind of a weird thing. So we saw this before, maybe with topological spaces, that morphisms of topological spaces can be given the structure of a topological space, and morphisms of abelian groups can be given the structure of a abelian group, but not for groups in general. Morphisms of abelian groups aren't groups, and morphisms of rings aren't rings. But this is a special type of category where we do have this. Okay, so the morphisms between R modules is itself an R module. Okay, one of the upshots of this, okay, is that for each M, each R module, M, which is an R module, right, we get two functors. Okay, so we get the functor H subscript M. This is the functor represented by M. Okay, this goes from modules to modules, R modules to R modules. So this is the functor. This thing is called the functor represented by M. All right, and we get another functor H superscript M. This is mod R, and then we have blank M here. And this is a functor from the opposite category. So I'm writing all my functors so that they're covariant from the opposite category of R modules to the category of R modules. And so this is the functor co-represented by M.
So if we look at homomorphisms between M and itself, is that kind of like the dual of a vector space in linear algebra?
Well, the dual of the vector space, yeah. So the analog, so your question was, so yeah, so the analog of the dual, and we actually call this the dual. I mean, let me just say this. Let me just write it out. The dual module. Let me just do an example, I guess. So it is, so we call this M here. So this is mod R, M R, like this. So this is the dual module. Yeah, so this is the kind of thing we're talking about. Yeah. So we're gonna do duality stuff. Okay? Okay. So let me give you the definition. Now that we have these functors, okay, I can give you the definitions of what an injective and a projective module is. Do you guys have any other questions? Module. Okay. I don't want to write this twice. Okay. Okay. So definition. So the first definition is of a projective module. So in our module, P is projective. if and only if this functor HP is exact. Okay, so this means so it preserves limits, but more than that, so I guess it preserves limits and colimits. Let me just say it's exact, and let me just use this definition. It takes exact sequences of R modules to exact sequences. Okay, so in R module, I is injective if and only if HI is exact. Okay, so this means that it takes exact sequences. Well, I mean, it's the same thing. Exact sequences of R modules to exact sequences of R modules. Modules. Okay, so all right, so this is the definition of what an injective and a projective module is. Okay, so let me just kind of spell this out a little bit more. So M is projective, or say P is projective. Right, and let me remind you what this is that if you know this thing here, 0 to V prime to V to V prime prime to 0, if this is exact, this implies that, well, this map here, 0, and then you do mod R P V prime, mod R PV to mod R PV prime prime to 0 is exact. Okay, and let me just remind you here, a sequence is exact, right, if the image of one map is the kernel of the next. Okay, so recall. So a sequence. You know, let's do, I don't know what we should call them. Let's do like this, dot, dot, dot. Or let's do dot, dot, dots first. VI, VI plus 1. Let's do VI. Two is exact if and only if, let's call this Fi and Fi plus 1. The image of Fi is the kernel of Fi plus 1. Okay? So this is what it means to be an exact sequence. And so in particular, right, that if this is exact, this is exact, you know, at V implies that J is injective. And this part being exact. This implies that, let's call this map P. P is a surjection. Okay, so okay, so that's what we had about this is what exact sequences were. Okay, so all right, so this is what projective means. Okay, and now we can talk about like what our freebies are, right? So there's another version of this, and it's actually like So half of this stuff is free. Okay. So, I mean, then you guys see that maybe I should write down the one for injectivity too. Okay. Injectivity reverses arrows, right? So the other functor, the one that's co-represented, all the arrows will be reversed. Okay. So maybe I can do that. Should I do that over here? Let me just make a little remark. Okay. Maybe I should say injectiveness, not injectivity, maybe. I don't know. How do you spell injectiveness? NES. Okay, so if this thing is exact, this is exact, right? This implies that, well, we just do everything backwards. So now, so we have mod R, and now we have V prime prime I, mod R, V I, mod R, V prime I, 0. Okay, so note that like this is exact. So in this case, everything gets flipped. Like injections go to surjections, and surjections go to injections. Okay, for in the injectivity case, or when you're doing the contravariant thing. Okay, so all right. So what are the freebies? Okay, so all right. So here are the freebies. So this just follows from like general categorical stuff, which we'll go over again. Okay, so we actually don't need to check that. Okay, so we know now that a module is projective if injections map to injections and surjections map to surjections, all right, under this map, under the one that's represented by P. A module is injective if surjections go to injections and injections go to surjections. Okay? All right, so it seems like we need to check two conditions to check projectivity, and we need to check two conditions for injectivity. Okay, this theorem is going to cut this down. So some of those are free. So lemma. Okay, let M be any R module. Okay, one is that if V prime F to V is injective, then the map here, so we can call this, then we'll write the map here, mod R M V prime to mod R M of V, and we'll call this map here, so we'll call this mod R M of F, and we use the notation F lower star for this. Okay, then this thing, so this is supposed to be above the arrow. So this is F star. So star. Okay, so then this is injective. So the freebie is that you don't need to be projective to take injections to injections. Okay. Similarly, if this map V F to V prime prime is surjective, then the associated map mod R M, so the other way around, we have M here. It flips the arrows. So F star. So VM is injective. All right. So we have two freebies. All right. So again, here F star. So this is defined to be equal to. So this is mod R F of M. So the functor applied to F. Okay. Okay. All right. So let's give the proof of this. So the proof is purely category theory, right? All right. So what's the proof? So let's do the proof of one. Okay. So this functor mod R M blank is a representable functor. Okay, and so what do we learn in topology? So representable functors preserve limits. Okay, okay, and also we want to recall that kernels are limits. Also, kernels are limits. Okay, so the kernel of F has two descriptions, right? So we have a map here. So the kernel is the equalizer of the map F and the zero map. Okay, so remember that limits are the terminal object of the category of cones, right? So you take a diagram, you make all the cones above it, and you take the terminal object before that. And then for this particular diagram here, this is called an equalizer diagram. Right? And this map here, 0 here, denotes the zero map. Okay? So in other words, the kernel of F is the equalizer of the zero map and F. So this is the equalizer. All right? So, okay. So the kernel, I'll just write it out in words here, is the equalizer of the zero map and F. Okay? All right, so since F is injective, so this means that since the kernel is a limit, right, the kernels must be preserved, right? Must be preserved under this functor. What we're calling it mod R M dash. Okay, so in particular, we have that. So we call this functor HM. All right, so this means that HM of the kernel of F is equal to the kernel of HM of F. And this is what we also called F star. Okay, so in particular, since F is injective, the kernel of f is 0. And so we have that the kernel of 0, so this is the kernel of hm of f. All right, and so this thing is 0. So this is the 0 module. This is mod r m to 0. The only map from m into the 0 module is 0, right? So it's the 0 module. Okay, and so this proves that HMF, this is this map f star, is injective. Okay, so as a freebie, right, we get that injective maps go to injective maps. Okay, so let's do the proof idea of 2. So the idea of 2. Okay, so the ingredients for this one are, you don't need that much, right? So you need to use, so here are the facts. Facts you need. Let me write it like this. It's the same exact idea, right? But you need to use the opposite categories. The opposite category, remember, it has the exact same objects, because all the arrows are reversed. Okay, so a morphism from A to B in the usual category will be now considered a morphism from B opposite to A opposite. So you just take the category and you reverse all the arrows. Okay, the facts you need is that one, or let's write it like this. Okay, is that f from V to V prime prime is a surjection. This thing is if and only if the co-kernel of f, which is defined to be equal to V prime prime mod f of V, is 0. Okay. The second fact that you need is that co-kernels are equalizers, or co-kernels are co-limits. Okay. So remember what a co-limit is that we took a diagram, and then we looked at arrows going out of the diagram, right? So we get these co-cones, right? And then the initial object in the category of co-cones was a co-limit. All right. So kernels are co-limits. In particular, the co-kernel of f is the co-equalizer of f in the 0 map. Okay, and the diagram associated to this is that you have f v to v prime prime. So you have these two maps here, and then you have the co-equalizer here. So this is f in 0. Okay, so this is the co-equalizer. It goes here, and this is the co-kernel. And this is really this quotient here that I wrote down above. Right. Okay. So the other factor that you need is that the other fact that you need is that limits. Okay. So limits in mod R. So these correspond to co-limits. So you just reverse all the arrows in the opposite category. In particular, co-limits in this category, these correspond to limits in this category. Okay, and then the last thing that you need is that if M and N are R modules, then the HOMs are opposite, right? So maps from M to N here. This is the same thing as the opposite category. So we have this op. Then we do M op. So now we have to flip it. N op, M op. Okay, so I claim that this functor here, so in particular, this contravariant functor, this seemingly contravariant functor here, right, is representable in, so the point is that this thing here, this is representable in the opposite category. All right. So maybe I should have done to make it. Okay, so these need to be okay to go along with the notation above. The M and N maybe should be flipped here, but that's okay. All right. So all right, but you guys see what I mean. This is the property that you need. Okay. All right. So just to summarize, right? So we defined what it meant to be an exact functor, right? And it seemed like we needed, so to check that something is projective, it needs to take this exact sequence to another exact sequence of our modules, right? And it seemed like that we needed to check that injections go to injections and surjections go to surjections. So there would be two properties that we would need to check, right? Well, as it turns out, injective maps always go to injective maps. That's a freebie. Okay, so as a consequence of this, we get that P is projective if and only if it takes surjections to surjections. Okay, similarly, for injective, we thought that we would have to check two conditions for I to be injective, right? We'd have to check that surjections go to injections and injections go to surjections. Okay, we don't. So this one always confuses me, but we get one of them for free, right? And it's that surjections go to injections. Okay, so as a consequence, so as a corollary, we get the following, right? We get that. Okay, so the one is that in our module, so P is projective if and only if. Again, I'm going to do some shorthand here. So mod R P of a surjection is a surjection. Okay, and two is that I is injective if and only if mod RP injection is a surjection.
I'm sorry, can you explain that notation a little bit? Because
This
P is a
notation here?
module. Because
Yeah.
mod RP surjection, because P is a module and surjection is a function, right?
Yeah, so
And
this is the functor applied to a surjection.
so it's
So
maps
you can
between.
apply a functor to a surjection. So what does this mean? Let me explain this notation. Yeah. So this notation means if for all let's say V to V prime prime here, let's call this P a surjection, then the map here mod R, and then we do P P V Okay, and now we apply the functor to the mod R. This is an R. P of, oh man, I did too many P's. Okay, let's not use P's. Okay, let's do F. F here. Here, this is mod R P to V prime prime, a surjection. Okay, so it does make sense to apply the functor to a morphism, right? So it's saying that this morphism is a certain type of morphism, and it says that this morphism goes to a certain type of morphism. Oh, and this is the wrong way, by the way. We have P here. P. Oh, sorry, this is I. And this should be an injection. Okay, so I is an injective module if it takes injections to surjections, and it takes and then this is projective if it takes surjections to surjections. Does that make sense, Liam?
Yes, thank you.
Okay, so all right, so there's another freebie here. So there's another terminology. So note that here's another corollary. Maybe, and this is just more reformulating what I've said before. So so for every m, an R module, the functor, well, let's do this. 1, so this thing here, mod R m blank is left exact. And then 2, mod R blank is left exact. Okay, now I need to explain what left exact means. So a functor, so here, what does this mean? So this means that, so here, let's take the meaning of this here. Okay, so this thing means that if 0 to v prime to v is exact, let's do this to v prime prime is exact, then this functor, so then this application of it, not doing hom, 0 to mod r p v prime, or sorry, not p, this is for any m. M mod r mv mod r m v prime prime is exact. Okay, so we get most of the sequence, but we don't get that this last part is a surjection. Okay, so we get these maps, but we don't get this last 0 at the end. Okay, and the other one says that if 0, so let's see. So we have that, so what do we had surjections go to injections. So if v prime to v prime prime to 0 is exact, then we have something like this. So we go 0 mod r. Okay, so now we do so we did the opposite way. Vm, and then v prime, this thing is exact. Okay, so we get yeah, so we go like this. Okay, so this is what it means to be left exact. So I'm not exactly sure. They might call this right. This is the correct property. I never remember if right exact is supposed to mean that this is the right sequence. This sequence ends on the right, or this one ends on the right. Either way, you're going to have a left exact. So this thing where you're missing the last zero on the right side, that's called a left exact sequence. And so either way, you're going to end up with a left exact sequence when you truncate appropriately. Okay. I think some people might call this a right exact sequence. All right. Okay. So, all right. So what's one of the things that I want to prove now? So I guess the next thing that I want to prove. Okay, so there's two things that we want to prove. So for next time. Okay, one is that so projective modules, or let's say free modules are projective. Okay, two is that every projective module is a direct summand of a free module. Okay, so there's this connection to free modules here. And I guess I'm going to give another version of what it means to be projective. Okay, so do you guys have any questions? Okie dokie. Poker faces. I will. Yeah, I'll hang around after class as usual if you guys have any questions. And I will see you guys on Friday.
Cool. Taylor, just like I guess in general, because of like the statement of this last thing we're gonna talk about next time, projective modules, the direct summand of free modules.
Yeah.
Is this related to like there seems to be not a lot or like analogous results for a lot of things related to something like that? Like we have a thing, and it's equal to a direct sum of like similar things, or like
Yeah. So like direct sums of injective modules are injective, direct sums of free modules are direct sums of projective modules are projective. But this thing means that so that F, so it looks like this thing's kind of weirder. This one's a little weirder. This says that P is projective. It's actually an if and only if. If and only if there exists an F which is free, such that F is isomorphic to P direct sum P prime for some other P prime. So you can like complete it into a free module.
Okay.
It's kind of weird.
Interesting. All right, cool. I was just kind of curious because like there's like like the statement is similar to a lot of other statements.
Yeah, it is. Like it's very like categorical, right?
Yeah.
So when there's lots of statements going around that are like very similar, it's usually because it's coming from category theory.
That's what I kind of figured is like this is like we're finally because like when I think about like I mean just in general like I mean like the Chinese remainder theorem is like a kind of result like this in my like poor understanding of things, in that like it's not exactly the same, but like we have like a ring being equal to the direct sum of certain things, and then we have another result relating to modules, I believe, in regards to that, and just like
it's a classification theorem.
Yeah.
Yeah, so
Kind of
that's what's going on is we're classifying projective modules.
Interesting. Yeah, I was just kind of curious as to how all that was like going together as I build up this knowledge base of things. So
yeah. They're that's a good way. I mean, it is a classification theorem. So yeah.
Cool. All right. Thanks, Taylor.
Yeah, no problem.